Welcome to our cooling tower and condenser water piping design seminar part 2. We are going to pick up today where we left off, and basically the sections we want to go through today goal-wise would be to see what the new ASHRAE standards that are becoming building code, energy codes, are doing to cooling tower piping, which is a good question. What is it and why should we be paying attention to that? And then we're going to summarize it with kind of a few little pitfalls, little common problems we've seen that kind of reinforce some of the things that we've learned. So, ASHRAE standards, what are we looking at? 90.1 2010 is the standard I like to refer to real quick and examine a little bit of how is it impacting condenser water piping, and what should engineers know about that, and what are the changes being caused by this. By the way, 90.1 2010 is out, and that's the one everybody's talking about. 2013 is also out. It has not been ruled on by DOE yet, but it eventually probably will be. But let's take a look at 90.1 2010. And the reason I'm focusing on 2010, it's the one that DOE, per this slide, examined and said it saves a lot of energy, and you can read it for yourself, it's pretty important, that every state in the union by October the 18th of 2013 should have an energy code that equals to or is better than energy usage in 90.1 2010. And this is what went out. Now, obviously, every state has not adopted it yet. I believe last time I took a look, maybe 9 states have already adopted this as in their building code. But a lot of cities are, and it's coming. So it may not be in your state today, but it will be eventually. It's the right thing to do. It's coming. It will be the energy code's basic standard for the country. And as time goes forward, it'll get stronger. Now, 2013 will be coming down the road shortly, but DOE, to my knowledge, has not ruled on that one yet. They're taking a look at it. At the bottom of this particular slide, you see a web page. Maybe one of the most important ones for you guys to remember. Go look at that web page. It'll tell you state by state what version of 90.1 you're on. And I think that's important for you to understand. Bottom line is we need to pay attention when this is becoming building code. It has. Whole federal code is this way already, and most of the states are beginning to look at it. And like I said, to my knowledge, 9 states have already adopted it, and it's coming down your way. So what is in 90.1 2010 that's the right thing for us to be looking at energy-wise as far as condenser water piping? Well, let's look at economizers right quick. I think the interesting thing on economizers is there's some changes here. Now, let's make sure you notice one thing. This is an air side or water side economizer statement. So first section of this on economizers clearly states any system with a fan, any system has to have either an air side or a water side economizer. It's got to be one or the other. Today we're going to focus on the water side a little bit because this is the part that impacts condenser water piping. But remember, it could be air side economizer or water side economizer, your choice. But what's new is what? Look at what's in red. The design capacity of the economizer shall be 50-degree dry above and 45-degree wet above and below. Wow, there's a statement of actual load. And you see some other comments about pressure drops allowed through the heat exchangers that you're using. Let's go a little deeper on this economizer thing. Where do you have to have an air side or water side economizer? And again, we won't be speaking about water side, but where do you have to have it in your design? Per DOE, per the energy code, per ASHRAE 90.1 2010. Well, if you read this statement pretty quick, it says the only exemptions I see would be climate zones 1A, climate zones 1B, no economizer required, or if your loads are smaller than 54,000 BTUs. 54,000 BTUs is what, about 4.5 tons? That's pretty small. So where would this exemption 1A and 1B climate zones be? Do you have to do an economizer where you live in the country? That's the question. Let's take a quick look and see what these climate zones are all about. Now, here's a map that if you haven't seen before, and you're in this business, you might as well get used to it. You're going to be seeing a lot more of this. What DOE did, they tried to define the country in climate zones. And then you're going to see me reference this a lot. And this is the climate zones that have been referred to in the standard. Now notice there's a black line down kind of through the middle of the country. Anything to the right of that black line is called the moist climate zone, or climate zone A. Anything to the left of that solid black line is climate zone B, or dry zone. And as you can see, it pretty well splits the country. Then you see numbers. Where can you find a 1A? Remember, and I'll go back so you can see that the exemptions were 1A and a 1B. Where is there a 1A? Only place I can see one is Miami, Key West. I haven't found a 1B yet. I don't even see one on the map. So it looks to me like, unless you're doing work in Miami, or that's where your project is, you have to do this economizer. Airside or waterside economizer has to be done. You got to take a look at it per this code. What else is in this economizer thing that we should take a look at? The first statement is one we said earlier, to give you the load. Look at what's in red there. The economizer shall be designed for 100% of the expected cooling load with an outdoor temperature of 50-degree dry bulb and 45-degree wet bulb. That's pretty specific. So what you'll be doing is, when you get your cooling load computer system running, you got your cooling load running, you need to take your cooling loads and dump in there 50-degree dry bulb, 45-degree wet bulb as a design point and get the load at that condition, because that determines the size of your economizer. The other thing I think that's really new, that's really catching people off guard, is the last statement at the bottom of this page, 6.5.1.3. Integrate the economizer control. The economizer system shall be integrated with the mechanical cooling. And keep reading it so that you can have partial economizer running at the same time that the mechanical cooling is running. In other words, you want to be able to run both at the same time. Translation. You want to be able to run the waterside economizer, you want to be able to run your chillers at the same time you're running your waterside economizer. You want them in series. You want them integrated. It's not either or. It's not on-off. You want to integrate the two so they gradually swing over. That is a huge change. And you need to be thinking about how you're going to deal with it piping-wise on cooling towers. We'll get deeper. So what are some other things? Simple little thing, but it's really something very important to the industry. You need to change your specifications today so that every plate heat exchanger that you use is ASHRAE. There's nothing proprietary about it. It just stops a lot of issues, and it's pretty much in the code. DOE's asking for it, 90.1's asking for it. So right now, if you don't need anything else, go to your specifications, put a guide in your guide that all plates shall be ASHRAE certified. Simple as that. You do it for chillers, you do it for cooling coils. Why wouldn't you do it for heat exchangers? Now, as I look a little bit deeper into 90.1 2010, I see some things that are going to impact cooling tower piping even more. Look at the pump head. Look at the bottom there in red. The pressure drop through each device and pipe segment in the critical circuit at design conditions shall be calculated. In other words, no more rule of thumb on a pump head for condenser water pump. We've got to do this right. We've got to detail it out, take it off, and do detailed pump head loss calculations. We maybe have a problem here. Just pay attention to this. It needs to be in the file. This is a change that we got to start paying attention to. Pump isolation, things pretty straightforward, but on a chiller and a boiler, if a chiller is not running, a boiler is not running, condenser is not running, you have to valve it off. You don't want water flow through a heat exchanger that's not doing any work. That's simple. If you look at water source heat pumps, nothing really new here. You got to have two position valves, and then they even become variable flow. So there's another comment you need to be aware of when you start looking at condenser piping and water source heat pumps. Look at the paragraph on variable speed. Any system over 5 horsepower, you've got to look at it if you can get 50% turn down. These are some things in 90.1 2010 you need to be paying attention to that in general impact the waterside design. Let's stay closer to a condenser piping. Let's say specifically on that, and you'll see why I'm bringing this up to you now. There's another section here on pipe sizing in 90.1, and in red there, it clearly states condenser water piping. Clearly states it. shall be sized per the values in table 6.5.4.5. So what am I telling you? I'm telling you there's a table now for sizing pipe based on the hours of operation. Here's the table. Brand new. Most engineers aren't aware of this yet. And it's already in the code, so you need to start being familiar with this. How will your firm, how will you deal with the code's requirement for minimum pipe sizes? And take note, the first column is based on 2,000 hours or less, other or variable flow. Other would pretty much be constant flow. Variable flow is what we speak of, obviously. But take a note, it would allow you to have smaller pipe sizes for variable flow than constant flow. In other words, the same size pipe on the variable flow can handle more GPM than on the constant flow. Look at the hours of operation. The more hours of operation, the bigger the pipe, or the smaller the flow. In other words, they're looking at it from a standpoint of operating cost based on pipe size and flow. And variable flow gives you smaller pipe sizes. This is why it's important you begin, again, to understand the impact. How are you going to deal with this? And you've got to do a detailed pump head loss calculation, and you've got minimum pipe sizes on condenser water piping. That is brand new. A couple other rejections of BTUs for towers. We won't worry about too much, but there's some numbers in here based on the minimum GPM to a cooling tower per fan horsepower of the tower. And here's an example for you in red. 90.1 2010 was 38.2 minimum GPM per fan horsepower through a cooling tower. Now, 90.1 2013, that number went up to 40.2 GPM. Now, I've seen specifications on the West Coast that number might be as high as 80 or 90 GPM per fan horsepower. So what they're going to do is they're going to make you have bigger boxes in your cooling towers, less horsepower per flow, and this is going to be the efficiency of the tower. So the impact, horsepower-wise, of a fan motor on a cooling tower is going to get smaller as we make the boxes bigger. And the energy code is going to drive this. You need to be aware of it. This is not hard to do. This is a matter of selection. But remember, there's a growing specification on the efficiency of the cooling tower based on GPM per fan horsepower. Where is all this taking us to with the economizers and these changes? I think one very important thing on cooling tower piping that we've got to slow down and figure out how to handle is this one. You may need 2 different cooling tower cold water supply temperatures. Wow, what am I trying to tell you? Waterside economizers, ladies and gentlemen, want the coldest water you can get. But the second paragraph, that gives you a hint. If you have a centrifugal chiller, it may not want water that cold. In fact, most of them don't. Now, this is a generic statement. We're not talking brands here. But you need to go to your particular chiller manufacturer and say, listen, I've got to do a waterside economizer. How cold of water do I put to your condensers? In most cases, it's going to be 65 degrees, maybe 50, 55 degrees is going to be a limiting number for head pressure control. You still got to control that head pressure on a centrifugal chiller or screw machine to make sure the refrigerant flows. So there's a minimum condenser water temperature coming from the towers for head pressure control. And that number is going to be higher than what you want for the waterside economizer. So you may need 2 different temperatures of water coming out of your cooling towers. Think about that a little bit. And let's go a little bit further with this discussion so you kind of understand. One thing that I wish I had an hour to do with this one slide, so humor me for just a minute. That red line is a constant load or temperature range. In this case, it's 10 degrees. So that red line on the slide gives you a constant load in tons on your tower, whatever it may be. The bottom axis is the wet bulb. And normally we pick a tower, phenomenal design. It's 78-degree wet bulb, which is what we call the summer condition here. It's 78-degree wet bulb, 10-degree range. So the first point we picked was a 10-degree range, by the way, is 3 GPM per ton. 15,000 BTUs, 3 GPM per ton, 10-degree range. So let's take a point, and I hope you can learn this one thing about tower. So please pay attention. A lot of people never quite grasp what I'm trying to get across to you now. What happens to the approach? What happens to the cold water temperature I can make in a tower as the wet bulb goes down? What happens? We're talking about cooling a building at 45-degree wet bulb and 50-degree dry bulb. What happens to that approach on a nominal tower that we pick for the summertime when we look at the wintertime conditions? What is that approach? Real simple. How cold of water can you make? How much of it? Well, with 10-degree range, I'm saying I got a constant load on my tower. The reason I'm doing that so you can grasp what's going to happen here is I lower the wet bulb temperature. Real basic, simple statement. Cold air holds less moisture. Cold air holds less moisture. A cooling tower is an evaporation machine. A cooling tower evaporates water. It is latent cooling. It's not sensible, it's latent. So I've got to evaporate that water. I've got to work with that wet bulb in the air to do this. I've got to take this moisture and evaporate it into the air. And I just said to you, real simple, hang on to this, it's very important for the rest of your life to understand this. Cold air holds less moisture. Go get a psych chart. Let's spend some time on this. But this is a lesson you need to learn the rest of your life. Cold air holds less moisture. Just remember that statement. And as you get through your life, try to figure that out. Let's look at what happens to a wet bulb situation on a cooling tower. Let's see what's going on here. So I'm trying to make what? 85, 95 degree water. Go to a summer condition. I want to make 85 degree cold water with 78 degree wet bulb. And my range is going to be 85 to 95, and I got a full load. All right, so if I'm making 85 degree water at 78 degree wet bulb, then my approach is 7 degrees. 78 degree wet bulb, I'm making 85 degree water, 7 degree approach. Slide that down to 50 degree wet bulb. Nice point to look at on the chart. And tell me, look at the chart, what water temperature can you make? How cold a water can I make with the same cooling tower, with the same load at 50 degree wet bulb? Well, let's take a look. Wow, it looks to me like I'm making, what, about 63 degree water? So I got 50 degree wet bulb. Now I'm making 60 degree water, 63 degree water. I've got an approach of 13 degrees. I got the same load, the same tower. I can only make 63 degree water with 50 degree wet bulb at the same tonnage on my tower. So what are you learning? Cold air holds less moisture. As I slide the wet bulb down, the approach on a cooling tower, anybody's cooling tower, has to go up dramatically at the same range, at the same load. Please hang on to those statements because it impacts your waterside economizer sizing immensely. How do you size your cooling towers? How much cooling you're going to get out of that cooling tower at 50 degree dry bulb and 45 degree wet bulb. If I slide under 45 degree wet bulb, I think you see 45 degree wet bulb making what, about 60 degree water. So I'm really looking at about a 15 degree approach on that same tower, same load, double the approach, same tower by lowering the wet bulb to 45 degrees. Let's go further with this. I hope you got that message. What does all this mean? Here's a typical piping diagram. You might note something here. I've got 2 sets of pipes. I got 1 set of pipe for the waterside economizer and a dedicated machine. I got another set of pipes for my regular centrifugal reciprocating machines, whatever they may be, for head pressure control. In other words, I've got a dedicated cell to the waterside economizer. In other words, I might have to run 2 pipes, 2 pieces of pipes. And you haven't been doing that. But you got to pay attention to head pressure control, and you got to pay attention to this because the code said what? Integrate. Be able to run the chillers at the same time you're running the waterside economizer. So that impacts how you do your towers. We're going to suggest this is probably what you're going to wind up doing. You make your own decisions, but this is what we're seeing a lot of people go to. So where do we put the waterside economizer to integrate? Now, in this slide, we're looking at the cooling tower side, the condenser water side, the 85, 95 degree side, the 15,000 BTUs per ton side. Now I'm going to switch over to the chill water side. On the chill water side, we're looking at the 12,000 BTUs per ton load. We're looking at the chill water side, the 45, 55 degree side. In other words, the water side economizer interfaces between what? Between the condenser water and the chill water side. So we got two sides to look at. Let's look at the chill water side of the water side economizer. What you want to do is get free cooling. You want to be able to provide chill water BTUs to the plant and save energy costs. That's what you're trying to happen. If I'm going to integrate the water side economizer in with the chillers, where do I pipe it? And I think everybody's pretty well agreeing, it's about only one spot left. It's not going to be in parallel with the chillers, it's going to be in series. So we're going to put it on the return chilled water side of the chiller plant. So here we go. Now the water side economizer is on a return water side, say the 58 degree return water. And I want to subcool that 58 degree water a little bit with my water side economizer before it gets to the chiller plant, before it gets back. Then my chillers are going to finish it off and make it 45. In other words, now I can turn the water side economizer on earlier, get more operating hours, and get a lot more payback than I could any other way. Let's take a little closer look at this as we go. So why would I want to put my water side economizer in series? Why would ASHRAE 90.1 specifically say integrate the water side economizer with the chiller so they can both run at the same time? Because by doing that, we get a lot more hours of operation. What does that mean? We got a lot more hours of higher wet bulb temperatures. We can turn it on. We can reduce the return water temperature back to the chiller plant. We can run it many thousands of hours more operating time than you can any other way. So now we're able to turn the water side economizer on higher wet bulbs. We may have to have two different cooling towers at water temperatures. Your chiller's not going to like 45, 55 degree condenser water, but your water side economizers love it. So you're going to have to make those decisions. Be aware, as you reduce your return water temperature, you're not reducing the total flow to the chiller side, but you're reducing the load on your chillers. If you're not careful, you could wind up short cycling your chillers because you still got to have the total flow, and we'll show you an example of this in just a minute, so just be aware there's a caution. And last but not least, ASHRAE is also talking in terms of elevate the chill water supply temperatures. In other words, can we take this 45 degree water and raise the temperature in the wintertime to a higher number and still keep everybody happy? The higher the supply water temperature in the wintertime, the more hours of operation the water side economizes. Your limitation, you still got to maintain humidity control. So there's your limitation. Just be aware, you're going to see a lot more discussion on that, and you need to be thinking about it. So this integration thing popped up, and I spent some time on it. Here's the wording again, and it very clearly states to provide partial cooling with the water side economizer, even when additional mechanical cooling is required. That's the key thing. That's the huge change you've got to deal with. I caution you about the possibility of short cycling when you do that, because your total flow rate to your load in your building has not changed, but you're reducing the supply, you're reducing the return chilled water temperature going back to the chiller plant. As the wet bulb goes down, you're able to take more and more of that with water side economizer, and you may wind up short cycling your chillers if you're not careful. The best way to show that is, this is kind of a busy slide, but take a few minutes. It's pretty basic, pretty simple. Trying to get this concept across to you, what's happening with the water side economizer when it's integrated in series with the chiller plant. Take a quick look. I've got three 500-ton chillers here. I'm using 12 degree delta T on the chiller, which means return temperature is at full load would be 57. At full load, the supply would be 45, 12 degree delta T, 2 GPM per ton. So 12 degree delta T, 2 GPM per ton, very good design, a lot of people using it. A 500-ton chiller would need 1,000 GPM. Two chillers would be 2,000, three would be 3,000 GPM of 45-degree water available. This is primary, secondary, just to show you so you can see relationships. Blue is cold, supply water, red is return of hot water. Very simple. So in this particular case, I've got a situation where I've got a 1,000-ton load going out to the building, 2,000 GPM at 485 degrees. I got a 1,000-ton load. I got 3 chillers online. I got a waterside economizer on the return, and my return temperature to the waterside economizer is 2,000 GPM, 57-degree water. But instead of dumping that 57-degree water back to the chiller plant, I'm going to take it down to 54 with the waterside economizer. I'm going to get 250 tons of free cooling by running that 57-degree water through one side of my plate heat exchanger, the other side of the plate through a cooling tower. I get free cooling, and I'm knocking down the return temperature to 54 degrees. So my chillers are not going to work as hard. I'm going back to the chiller plant now at 54 degrees versus 57. Do you see that? And when I do that, I take the load down significantly. And as you can see, as the waterside economizer works harder and harder and harder, that return temperature goes down. So let's go to the common pipe and see what happens at the chiller plant. So now I got 2,000 GPM of red hot water, 54-degree water coming back. And as you can see, it's mixing with 1,000 GPM of 45-degree chill water at the common pipe to give me 3,000 GPM of 51-degree water going back to my chillers. So each chiller is seeing 1,000 GPM at 51 supplying 45, 6-degree delta T. So what do you see? The design is 12. Each chiller is doing a 6-degree delta T. Each chiller is 50% loaded. Everybody's happy. It would be not unusual to run 3 chillers in this situation because most machines would be more efficient around 50% versus running at some higher number. You've got to make that decision based on your chiller load profiles. But here's my question to you. What would happen is that 51-degree water go down? What would happen is my waterside economizer takes 500 tons of the load. The total load of 1,000 tons on the building, the 2,000 GPM to the building stays the same. But as my waterside economizer gets lower wet load, it works harder and harder and harder. So instead of taking it from 57 to 54, it may take it from 57 down to 51. It gets more and more work being done. You're going to lower the water temperature going back to the chillers, and you're going to create short cycling if you're not careful. In other words, you cannot stage these chillers based on flow. You cannot stage these chillers based on flow of the cooling load. So the cooling load 2,000 GPM didn't change. You're going to have to stage these chillers based on actual load. You may have to do some chill water supply reset temperatures in order to make it all work out. We can talk more about that later. Just want to caution you with that because it's an area that people who try this for the first time I have a little bit of trouble with, and I'm trying to make sure that they grasp it. So how do you do a waterside economizer? What are the things you need to be aware of? Calculate your cooling load. You got your points that to work on. You got 50-degree dry bulb, 45-degree wet bulb. You're going to put them in series or parallel. I think you got to go series integrate. Maybe you can figure parallel out, but I think it's going to be series. Your decision. Cooling tower pipe. One or two sets of pipes. You're going to have a dedicated cell. What is your required chill water supply temperature? What is the approach going to be to your tower? What wet bulb are you going to size your heat exchange in your tower on? You also got to look at the wintertime operation. You got to look at 50-degree dry bulb, 45-degree wet bulb. That's how you're going to size your heat exchanger. And you need a control sequence. Here's a typical control sequence that a friend of ours is using. I think the bottom line of all this, he's using a dedicated cell for the waterside economizer. He's turning on that waterside economizer dedicated cell anytime that the wet bulb temperature is 5 degrees below the chill water return temperature. That's the magic. Anytime the outdoor air wet bulb temperature is 5 degrees below the chill water return temperature, you can save a bunch of money by starting to integrate the waterside economizers in with the chillers. It's a snapshot of how you see a dedicated cooling tower cell to the Waterside economizer. As we've been showing you, this system works, and it's the same thing to integrate the code. This is how you get it done. Let's look a little bit piping. We kind of talked about economizers. I'm going to take just a 30-second break right here. I'll pick it right back up. Hope that didn't bother anybody too bad, but the old man's fighting a little bit here. So Chad, we're going to edit this out, and we're going to just start right back in 5 seconds. Now we'll look at suction piping. Piping is something that we wanted to make sure we looked at, and we've covered a lot of pieces of it, but we're talking about cooling towers, so we've got to look at pumps a little bit in suction piping. When you do that, keep in mind that a cooling tower aerates water. So the water in the basin of a tower is full of air. It's full of air as you can get it. In fact, the 100% efficient tower would be just full of air. It couldn't take any more. So if I drop the pressure in it all on that water in the basin of that tower, air's going to start popping out. So my suction piping has to be taken into consideration the fact that I might have air in it. How would I handle it? So suction pipe on a tower, you want your eccentric fittings on the top of the pipe, flat on top. You want your reducers on the bottom. You want to keep it as straight as you can, and we want straight pipe running into it, velocities down. And a rule of thumb we give everybody is to keep the pressure drop between the tower and the suction flange to 5 feet. Now you can do what you want to, but it's kind of a rule of thumb. But remember, any pressure drop on that water, you're going to get air out. That's the thing you need to remember. A cooling tower aerates water for a living. A cooling tower aerates water for a living. If we reduce the pressure, that air is going to come out. So in piping, we like 5 to 10 pipe straight pipe. The little bottom picture shows that air pocket. That's bad. You don't want any part of that. That's where the air is going to collect. You get a big bubble of air coming out into the pump. You can take stainless steel shafts on a pump and bring them into it. I've seen an 1.5 inch stainless steel shaft completely rung into it because of a bubble of air. You can't make the shaft big enough. It's impossible. A pump's centrifugal pump pumps water, not air. You've got to run the load pumping water, and you give it a bunch of air, you're just going to tear it up. Anybody's pump, you just will not handle it. So you've got to keep the air out of it. I think this picture is worth a lot. Hope you recognize this picture. Is not your job, obviously, but eccentric square on the bottom. Where should it be? On the top. They had air problems. They had air problems on the suction side of the pump. What did they do? They put gauge tappings in the tops of those little eccentric fittings to get the air out. But you know what? They had a slightly negative pressure and more air went in. They had a daggum nightmare. This is the one I was telling you about that broke the shafts into. And it ain't our fault when you do things like this, guys. You got to help us out a little bit. You got to recognize it's not unusual to have slightly negative pressures on the suction side of a pump. And you're going to always have air. So those are 2 things you got to deal with, and we can't change the basic laws of physics. Hopefully your jobs never look that way. Here's a typical example of what I was trying to give you. Look at a cooling tower at Myrtle Beach. And we're just going to look a little bit at MPSH. I wish we had an hour on that, but we don't. We got another YouTube, by the way, if you want to look at MPSH, go on and take a look at it. But here's a cooling tower at Myrtle Beach, no hurricane, 0 PSIG, 85-degree water. And let's just look at a typical piping of a tower. Now, let's assume that the tower is elevated 2.3 feet above the center line of the pump, okay? Let's assume there's 4.6 feet of pressure drop between the tower and the section of the pump. Got that one? Now, I got gauges underneath the tower and a gauge at the pump. Let's turn the pump off. So with the pump off, what would those gauges read? With the pump off, I got elevation 2.3 feet. I've got a gauge reading positive 1 pound. And the gauge on the suction side of my pump with the pump off is going to read a positive 1 pound. Now what happens when I turn the pump on? Well, I got this friction loss of 4.6 feet. By the way, I think everybody knows this. 2.31 feet makes a pound of water, specific gravity 1. So when I turn the pump on, my suction gauge on the suction side of my pump is going to become slightly negative. It's going to lose 2 pounds because of friction loss. So I had a positive pressure of 1 from the elevation. I lost 2 pounds running through the friction. So the suction gauge now reads a -1 if it's a compound gauge. So one of my pet peeves to everybody listening to this, make sure all your cooling towers have a compound gauge. It's not unusual for us to go on a job site and we see gauge read 0 because it's not compound. And yet it may actually have a negative pressure. People telling us the pressure is 0. Well, if it's not a compound gauge and you got a negative pressure, how are we going to know it? So first pet peeve, make sure. So this would not be an unusual situation, would it? Does this problem have, this cooling tower at Myrtle Beach, does it have an NPSH problem? It does not. Slightly negative pressure, you may get a little air out of solution, but you remember you were pumping 85-degree water. So what would it take for 85-degree water to boil? Take a real negative pressure, -1 pounds. It's not going to make 85-degree water boil. Probably a negative 13 pounds, 14 pounds, that ballpark, to get 85-degree water to boil. Bottom line, the available NPSH is 31 feet. There's really nothing wrong with this application. I don't like the negative pressure, but it's not unusual. This is a typical cooling tower, no NPSH problem at all. If you want the rule of thumbs again, leave the suction lines alone, please. Keep the pressure drop between the suction of the pump and the tower defined all over 5 feet. Please keep it clean. If you got any valving, put it on the discharge side of the pump. A little bit on the discharge pipe. And this is another little pet peeve of mine, called a water leg. And we got a triple duty valve on the pump here. And I turn that pump off. Where's the water going to go? I hope everybody sees where the water went. That water leg is trapping the water. So all the discharge piping, all the condenser water piping is full of water with the pump off. So how much water went into the tower? The water went into the tower was in the hot decks of the tower, the fill of the tower, a little bit of overhead piping. But it was not enough to flood the tower. Everybody's happy because of the water leg. You turn the pump back on, you got plenty of water to get everything going again, there's no problem. Now, let's look a little bit of discharge piping. First of all, you saw that ASHRAE 90.1 2010 now defines the minimum pipe sizes on condenser water piping, so you might as well get used to it. You do need to allow a little bit for future fouling and pipe corrosion. What's a reasonable number? You decide. 5 to 10 feet safety factor is what I see people normally doing. It is reasonable to assume that an open system like a cooling tower, that the piping over its pipe life is going to foul some and you will pick up a little additional pressure drop. If you got horizontal piping, as we showed you in that drain down thing, make sure there's a water trap or it's below the tower. And we'll look at that picture again in just a minute. Make sure you got non-slam center guided check valves on the discharge of your pump. Want to make sure they don't leak back. You got to make sure you got good quality check valves. Triple D valves work right here. Install a pipe filling line above the check valve if you're worried about trash, so you can keep everything primed. Now, we kind of went through the discharge piping pretty quickly there, but that was the point, and you've got to follow the codes, and you want to make sure you don't drain them down. We're going to show an example of a problem in a few minutes. Let's look a little bit quick at cycles of concentration because it's in the code, and for the first time. And a lot of engineers and people have never really dealt with this. They've heard about cycles of concentration in a cooling tower. In other words, as I evaporate this water off in a tower, what I call the rocks stay behind. So sooner or later, I've got to have some blowdown water going on down the drain, or my tower's going to cake up as one great big rock. And this is determined by the cycles of concentration. So what I like to try to do here real quick is, if you people have never really looked at cycles, it gets you to understand what it is. Here's a formula for it. And it's based on the blowdown rate of the tower versus the evaporation rate. And if the blowdown rate is equal to the evaporation rate, you got 2 cycles of concentration. So let's just walk through this real quick. You got a formula, but see if you can understand a little quick rock story of what cycles are, because you need to begin to think about this because the code for the first time is specifying the cycles of concentration on your cooling tower, and you're going to have to deal with this. Well, I get my cooling tower going to the left-hand side. I got all this water in there. Let's just take all these solids, just make it one big rock, okay? So we got 1 cycle of concentration when we start off. We got 1,000 gallons of water in that tower. We evaporate that water down, we got 1 rock. Okay, great, that's good. But when we evaporate that 1,000 gallons of water down to 1 rock, what are we going to do with our cooling tower? We're going to make up another 1,000 gallons of water. And when that other 1,000 gallons of water comes in, it brings another rock. And I've now got 2 cycles of concentration. I got 2 rocks and 1,000 gallons of water. I evaporate that 1,000 gallons of water down again in my cooling tower. My 2 rocks stay behind. And what do? You bring another 1,000 gallons of water in with another rock. I got 3 cycles of concentration of 3 rocks in 1,000 gallons of water. If I evaporate that 1,000 gallons of water all the way down to the bottom, my 3 rocks are still there in that tower. But what are you going to do? You're going to bring in another 1,000 gallons of water. And what comes with it? Another rock. And now you got 4 cycles of concentration or 4 rocks. That concentration is that simple. I'm just trying to get you to understand what happens in the process. As you can see, if you don't have some extra makeup water, you're going to wind up with a tower full of rocks. Sooner or later, you just can't keep going. So we got to learn to deal with cycles of concentration. Here's a quickie chart to make the point to you. This is basically a 1,000-ton blowdown example of evaporation and blowdown and total makeup water required to a tower based on the cycles of concentration. Ladies and gentlemen, water usage in this country is becoming more critical. Whether you like it or not, we're going to be dealing with this for a long time to come, and the codes are going to get tighter and tighter and tighter. The old days of just blowing a tower down, not paying any attention to how much water are gone. You're going to have some system to control the cycles to manage and save as much water as possible. Reasonable cycles for concentration in cooling towers probably 4. Let's just get a quick example of what's going on. But most of the towers I've seen up recently, people just had a manual valve blowing them down, and with nobody looking at the actual conductivity of the amount of solids in the tower. So here we go. If 100-ton tower, the evaporation rate required, 15 pounds roughly per ton, for 100 tons, it stays constant. It's 180 gallons per hour across the top, all the way to the 10 cycles on the right. So this is a plot of the makeup water required in gallons per hour versus cycles of concentration. And the message is, at 2 cycles of concentration, remember the evaporation rate of 180 gallons per hour is exactly equal to the blowdown rate of 180 gallons per hour, or we need 360 gallons per hour on a 100-ton load to maintain 2 cycles of concentration. Now, as I increase the cycles of concentration, what happens to the total usage of water? Notice the evaporation rate has to stay the same. Cooling towers need 15 pounds of water pretty much per ton evaporated to keep them working. That's fixed constant. So the 180 gallons per hour evaporation rate stays the same. But as I increase the concentration, as I increase the number of rocks, the amount of water I'm blowing down goes down. So at 4 cycles of concentration, I'm blowing down 60 gallons per hour. My evaporation is still the same. My total water usage is 240. All the way out to 10 cycles of concentration. Evaporation rate is still 180 gallons per hour. The blowdown is down to 20. So I really got a lot of rocks. I'm 10 cycles of concentration up to 10 rocks. What are you seeing? The total water usage is flattening out. The amount of water you save by increasing the cycle concentrations goes way down as you increase it. In other words, going from 2 to 4, you save a lot of water. Going 4 to 10, you save very little water. So to get way out to the high levels of cycles of concentration doesn't make a lot of sense because it's hard to do. You're living on the edge. It's hard to maintain those high levels of cycles of concentration, and your payback and the amount of water you would save is not there. So what are reasonable cycles of concentrations to specify? Good question. Here's an answer for you. ASHRAE's 189.1, so-called Green Building Code, the one the Army Corps of Engineers adopted, the one a lot of cities are adopting, you're going to see a lot more of, defines the cycles of concentration. It's the first time I've been able to find in ASHRAE any kind of code or standard recommendation on cycles of concentration. But here it is. Take a look. If you've got less than 200 parts per million of solids or rocks in your water, minimum 5 cycles of concentration. If you're out west, you've got hard water, you're over 200 parts per million, 3.5 cycles would be a concentration. The point is, you're going to be asked to control your blowdown rates based on cycles of concentration. Here's another little comment from this ASHRAE 189.1. And you see you're going to have some conductivity controls, and that's going to be a given you're going to have to do. But look at item C. Look at item C. Any condensate from air conditioning units over 65,000 BTUs, that's 5.5 tons. You've got to collect it and reuse it. Now this is ASHRAE 189.1, excuse me, the Green Building Code. The one the Army Corps of Engineers has already adopted. A lot of cities have adopted. This is 90.1 and 189.1. But it's coming. And if you want to play with this, you need to understand it. But it's telling you if you want to build a building per the Green Building Code, which a lot of people are doing, this, you're going to have to do this. What are you going to do with that condensate? So it's interesting comment, any cooling coil in your building over 5.5 tons, you've got to collect that condensate and reuse it. Think about that one a little bit. So as we summarize this and bring it all together, and we appreciate your time, let's see if we can go back to part one and repeat a couple little things that might be of interest to you. Let's look at some little common pitfalls. People seem to have fun looking at things like this. So let's look at low flow multiple cells. Remember dry air disease? Let's take a quick look. Here is a large process plant with 6 1,000-ton cooling towers on it, actually located physically in South Carolina. But remember, we said up until 90.1, cooling towers did not have any kind of minimum turn down requirement. So most towers would turn down, maybe let's say in this case 35%. Remember 90.1 2010 now states all cooling towers have to have a turn down to 50%. So if you're specifying ASHRAE 90.1 2010 on cooling towers, they've got to be able to turn themselves down flow-wise to 50% of design capacity, not having any troubles. Well, the old towers would not necessarily do that. In fact, the vast majority would not do that. So here's the situation. What about guys who are a good friend of mine, by the way, his last name is Leak, I don't hold that against him, but a guy selling pumps named Leak. It's kind of funny to me, but that's what he does for a living. But anyhow, long story short, he's sitting here, he's working with low flow multiple towers. He gets a phone call and he goes out here and takes a look at this plant. What does he see? Well, he gets a phone call and the owner says, I cannot maintain 85-degree water even when I'm only running one chiller with your towers. I'm not producing. Now, look at this. You got minimum turn down of 35%. That means the minimum flow rate to any one of these cells is 1,950 GPM. Design is 3,000, but the minimum is 1,950 for them to work. You got 3 chillers, 2,000 tons each, 6,000 GPM each. So what did our guys find when they got to the job site? Take a quick look. Now, do you see what you got right now? What did they find when they got there? Yep, that's what they found. Make sure you didn't lose the picture here. They found 1 chiller running, the other 2 valve off, and all 6 cooling towers. All 6 cooling towers running. 6,000 tons worth of towers, nominal, on 1 2,000-ton chiller. And they couldn't maintain conditions. They couldn't keep the chiller on line. Why? Wow, low flow. Are you telling me, Chris, there's only 1,000 GPM per tower? Correct. Minimum allowable was 1,950. We got dry air disease going on. How would you fix the problem? Well, what you got to do, obviously, is valve all 3 machines. If I valve all 3 towers, if I cut off 3 cooling towers and keep the flow rate the same, I'm going to wind up with a total flow of 6,000 GPM with 3 cooling towers. If I cut 3 of them off, keep 3 running, I'll wind up with a flow rate of 2,000 GPM per tower. And the minimum was 1,950. That's what we did. Worked like a charm. And the bottom line was, they've been running that way for years. They've been paying a lot of money for it. These towers had that dry air disease. This is a common problem. They were tearing the towers up. The KWs were ridiculous. They were having to rebuild the towers. This is a real problem. Please wake up and realize this is not chemical treatment. This is a real life situation you need to work on. Here's another one for you. Might be a little fun. Tower floods at shutoff. What would cause that? There's something on anybody's tower called pull down volume. That's the amount of water in the field and the hot decks, a little bit of overhead piping. And the sump of the tower is designed to hold that pull down volume. It'll hold it nicely. So that's the design. What would cause a tower to overflow? Well, if you pipe a tower like this, you're going to get overflow. In other words, take a look. This tower is designed for pull down volume, but not for the water in all overhead piping, not for the water in the condenser, not for the condenser piping. And all that piping is above the tower. So in this case, when you turn the pump off, all the water in the condenser, all the water condenser water piping does what? There's no water trap. It drains into the tower, goes out the overflow, and it floods the parking lot, and you blame the tower manufacturer. Well, you can't do all that overhead piping and all that condenser water piping above the tower and have it all drain out. The sump's just not big enough and doesn't make a lot of sense. Now, what do you do about this? Well, what happens when you turn the same pump back on? Remember, we drained all that water out of that piping. We got to refill the condenser. We got to refill the condenser water pipe. So when we turn it back on, the sump runs dry, and we don't have enough water to fill the pipe back up, and we cavitate our pump and turn our pump up. Because you pump down the water and you take the hole in the cold water deck of the tower and you pump it completely dry because you don't have enough water. What's the solution to those two problems? A water trap. Remember that water trap, if you do it properly, out close to the tower. It's just a piece of vertical pipe running up above the tower to make sure you trap the water in the condenser and the horizontal piping. When you turn the pump off, as you recall earlier, it traps the water at that point, and you stop the overflow. Water going out the parking lot, you stop the water overflowing, the overflow. And when you turn the pump back on, you also stop it from pumping everything down and starving it. Real simple application. Here's one more, and we'll call this the last one I want you to take a look at. Air trapped in the suction pipe. This was a young designer who didn't know any better, and here we go. What do you think you want to do with that? Here's a cooling tower, and for some reason they decided to put a road between the tower and the equipment room. It's like a little car running through there. Look at that, it runs right through the piping. I think you kind of got the idea, but the point is, we've got this piece of overhead piping overlooking the road and going back down, and when you turn the pump on, what happens? I hope you recognize that that tower is open. So how are you going to make this work? Well, they called me up and said, get out here, Chris, fix this pump of yours. It won't even pump. We can't even get water to it. I get out there, everybody's kind of laughing. They see the problem. But obviously, you turn this pump on, there's no water above the road. That whole piece of vertical piping there is trapped with air. What are we going to do about it? Obviously, bad design. Obviously, better off to take that piece of piping, put it underneath the road, and make it go. But they wanted to make it work that day. They wanted it to work that day for some period of time. What would you do? How would you get it going? This is what we did. We got a pipe fitter, a good friend of ours, that goes stand in the base of that cooling tower over there with a piece of plywood. So it's a bottom outlet tower to the left. We cut a piece of plywood and put it over the bottom outlet of the tower, and got a guy to stand on that piece of plywood to try to keep the water from going out the overflow that we're putting in there. We went to the top of this air trap and put a big air vent. And we put a hose, a garden hose, that we could just pump water in there. So what we did was we were trying to get the air out of that piece of pipe above the highway there and get it full of water. Now, as you put water in the piece of pipe that's above the pavement, obviously it's going to try to drain out through the cooling tower. Therefore, we had a guy standing in there with a piece of plywood trying to hold the water back in the tower. As we did this period of time, we were able pretty much to get water up into that piece of pipe and get a lot of air out. Now, what we did then was we got to get the guy at the cooling tower out with that piece of plywood and turn the pump on at the same time, which is what we did. We yelled, got the plywood out of the bottom of the cooling tower, he jumps out, and we turned the disconnect switch, turned the pump on, and we called it flowing. In other words, if you can get this overhead piece of piping primed, if you never get water to it, you can make it work. Now, you may have some cavitation problems, you may have some air problems, but if you can get the water flowing through there one time and keep it primed, you can make it work. And we got it going that way. The problem is if you ever turn the pump off, if you ever lose that prime, if that overhead piping ever drains back into the cooling tower, it's going to be airbound again. Bottom line is, don't ever do that. I like my little car, and I think you know not to have those kind of problems. So, ladies and gentlemen, we had a little fun with this. I hope it's something you never would do, but we appreciate your time. Let's take a quick look at something that's worth you taking back with you. As we do seminars, we're trying to educate people on two different types of towers. There's a counterflow tower and a crossflow tower, and both are great designs. But with your pumping head, your piping head, and all the new codes, you're going to have to calculate detailed pump head loss calculations. You're going to have to run yourself through it. Recognize, on counterflow towers, there is no hot water deck. The spray nozzles, and those spray nozzles need 3 to 6 pounds of pressure to work. On a crossflow tower, you got hot water basins that flow by gravity. The message is the counterflow tower has to have 3 to 6 pounds more pressure on your condenser water pumps than crossflow. At 3 to 6 pounds of pressure, maybe 10 to 15 feet of pump head, don't come up short. You got to do a detailed pump head loss calculation on your towers. Listen to me, please. Take the time to account for the pressure nozzles. You're going to need a safety factor on both, fine, but you can't hide behind the safety factor. You're going to be short if you don't take the time to recognize the difference in the counterflow and the crossflow designs. Both work great, but recognize the pump head requirements on the counterflow will be higher. Ladies and gentlemen, this is a counterflow tower with the pressure drop. You see the spray nozzles through it, and the air's coming from the bottom going up. Water's coming from the top down, so therefore it's called counterflow. This is a piping seminar. What we're trying to teach you is you've got to put that 3 to 6 pounds of pressure where? Into your pump head loss calculation. Just that simple. In a crossflow tower, you do have hot water distribution, and you have hot water basins and just gravity flow. So you don't need the extra 3 to 6 pounds there because gravity takes care of it. So if you kind of look at all this counterflow versus crossflow, we kind of put this in here to give you a picture of this. It can be a pretty significant operating cost difference between the counterflow and the crossflow if you start looking at that pump head loss calculation required for the counterflow tower versus the crossflow. The main thing I'm trying to get across to you, don't come up short. ASHRAE says you got to do a detailed pump head loss calculation. When you do that, account for this to make sure you got the right pump head on your condenser water pump. Thanks for tuning in. Have a great day.